Hi, welcome back. I'm welcoming you all to this online learning platform, Unacademy. So all of you know that Unacademy is the India's largest online learning platform. So I'm welcoming you all to this beautiful online learning platform. Now we are happy to announce that now Unacademy is going to providing support to the students for who are preparing for their GATE and service examinations. Okay, now we are requesting the students please utilize this beautiful facility to you which is provided by the Unacademy. Okay, now India's top educators are going to be handling the classes in this, most experienced faculty who are best in IITs and who are already success in IAS. Okay, those members are handling your classes. So please utilize this facility and get success in your examinations. About myself, I G Venkata. I have 16 plus years of teaching experience. So far I mentored more than 60,000 students for their GATE examinations, and at present I am pursuing PhD from JNTU Kakinada. My specialization is VLSI domain. Now, first we check how to get the Unacademy learning app in your device. Just go to Play Store, there type Unacademy, then you get the Unacademy learning app like this. Okay, then you get the app like this. Just click on this install button. It will install the Unacademy learning app into your device. Once you open the device, there you get what are the different courses available in that and who are the top educators handling the different subjects in that. And in addition to that, you get the brief introduction about that educator, means that faculty also who are handling the classes. Now here I am showing some of the top educators who are handling the classes. Tiwari, he is the IIT topper, and Mr. Ankit Goyal, he is the All India topper 2 times in GATE electrical department, and he got gold medal in IIT Indore. Okay, next Jain sir, he is the top faculty from CSE side. He is most experienced faculty. Is the and Jaspal Singh sir, he is the ex-IAS officer. He got All India 4th rank in IAS, and a few more faculties here I am showing you. These are the top few of the top faculty from different departments, and they are going to handling different subjects. Okay, and next we are happy to announce that recently we started two new batches, one for GATE 2022, other one is for GATE 2023 for different disciplines. For mechanical engineering, there is a Ascent batch for GATE 2023. This batch started from 8th February 2021, and here are the top faculty who are handling the subjects in this. And next, there is a Evolve batch for GATE 2022. This batch also started from 8th February. Here are these top faculty who are handling the classes in this. So the faculty who are taking the classes for GATE 2023, same faculty handling the subjects for GATE 2022 also. And in civil engineering point of view, this batch also started from 8th February. There is a Ascent batch for GATE 2023. Here are the top faculty who are handling the subjects in that. And there is a Evolve batch for GATE 2022. This batch, this is in civil engineering side. Okay, here are the top faculty who are handling the subjects in this, and this batch also started from 8th February. Okay, now there is a Evolve batch for GATE 2022. This is for computer science and information technology. This batch started from 8th February 2021. Okay, next. Now we are moving to electrical engineering. In electrical engineering, there is a Ascent batch for GATE 2023. Okay, this batch started from 1st February 2021. Here are the top faculty who are handling the subjects in that. And next, There is again a Ascend batch for GATE 2023. This time this is for Electronics and Communication Engineering. This batch started from 1st February 2021. Okay. And again there is a Evolve batch for GATE 2022. This time this is for Electrical Engineering. This batch started from 1st February. And again there is a Evolve batch for GATE 2022. This batch started from 1st February. This is for Electronics and Communication Engineering. Here are the top faculty who are handling the subjects in this batch. Okay. Now we are moving to Chemical Engineering. This batch started from 25th January 2021. Okay, here are the top faculty who are handling the subjects in Chemical Engineering. And at outside it is very difficult to get the Chemical Engineering training for GATE examination. So Unacademy gathered the top faculty, top educators in Chemical Engineering. Okay, they gathered all those and they are providing such a beautiful facility of providing training to Chemical Engineering students. They must thank to Unacademy to providing such a beautiful facility to them. Okay. Next we are moving to what are the, just we look at what are the different engineering disciplines available in Unacademy for GATE and service examinations. Now, mechanical engineering, electrical engineering, computer science and IT, civil engineering, production and industrial, instrumentation engineering, chemical engineering, and electronics and communication engineering. These are the different engineering disciplines available for GATE and engineering service examinations. So next, now we are moving to, there are two subscriptions in Unacademy. One is a plus subscription. Plus subscription is the basic plan. It is the basic plan. And iconic subscription is the, it will take this iconic subscription, take the your GATE and service examinations preparation to the next level with personal coach. By providing a personal coach to you, it will take that one to a next level. Okay, now in both the case there are few commonalities. India's best educators are handling your classes, interactive live classes are there, and structured courses and PDFs are available. Structured courses and PDFs, live tests and quizzes are available. Okay, now we differentiate this iconic from plus plan is by providing a personal coach. Now the purpose of the providing personal coach is, once you've written some exam, that exam paper is going to be analyzed in detail. Okay, after analysis they will prepare a note on that, that is where you are strong and where you need much preparation and where you are doing mistakes. Okay, such type of things they will analyze and they will provide a proper solution to that. Okay, and that means by in the form of by providing a study planner to you and respect to material to you, they will fulfill that gap. Once that gap is fulfilled, okay, by writing more number of tests you can check your negatives where you are committing mistakes multiple times, and based on that data they will fulfill the gaps and they will make you ready for the examination. That is the intention behind the providing a personal coach to each and every individual student. I'm stressing that, not for a complete batch. For each and every student, individual student, we are providing personal coach. Okay, so that is the importance of this iconic subscription. Okay, now if you check this, just we click on to this plus plan. In plus plan there is a 1 month subscription, 3 month subscription, 6 month subscription, and 12 month subscription, 18-24 month subscriptions also available. But as a faculty I am suggesting the students, minimum take 12 months subscription, but the 12 months is required for a student to listen the complete course and to prepare the complete course and sorry, and write some more number of examinations in that, and they identify the gaps where they are doing mistake, where we are confusing in exam while we are entering into examination mode, where we are committing the mistakes. Okay, to identify those gaps they need 1 year of time, and after that identifying those things you have to fill that gaps and you can ready for examinations. That is the reason why we are saying minimum 12 months is required for a student. Okay, if you don't have much time you can go for these subscriptions also, 1 month, 3 months and 6 months also. And by using this my code VROUT10 during subscription you get 10% discount on this 30,250 rupees. After this discount it became 27,225 rupees only. And if you observe one thing, this amount of 27,225 rupees what you have, this is approximately a little bit amount, more than 2 to 3,000 more compared to the transport charges what you are spending. Okay, what you need to spend to travel from your home to the outside location where you are taking the training for GATE if you join in offline. Okay, so a little bit difference. Now I am talking about transportation charges, not the fee what you are paying to that that institution. Okay, just with the transportation charges itself you get that facilities more than that what you are getting there. Okay, so my dear students, think think of it, and most important thing here is every day minimum 1 hour for traveling and to go there, and to move from that one to your home another 1 hour, total 2 hours of time you need to spend for transportation. Now the 2 hours is sufficient for a student to rewind the subject what we are going to covering on that day to you. Okay, so please my dear students, please think once of it. Okay, save your time, save your energy by staying at your safely at your home itself. Okay, get the more benefits. Next we are moving to iconic plan. Now here it is available for EMI option, also available for both the plus and iconic plans. Okay, just a minute. Sorry. Now so there is a 12-month subscription with the cost of 50,250 rupees. Okay, now the cost of this one is 50,250. By using my code VROUT10 during subscription you get it by 45,225 rupees. And there is a 2-year subscription, it is 74,000. Okay, with a discount of 10% it became 66,600. For third year students this is the suggestible, and for second year students this is the suggestible one. And don't forget to use my code during subscription VROUT10. Okay, by getting that code during subscription you get maximum benefits of 10% discount. Okay, and so now you observed or not, this is the amount what you are paying, approximately little bit close to the amount what you are paying at outside institutions. Okay, just by paying this much amount only you get the benefits. India's top educators are going to be handling your classes, plus personal coaches available. Once you written exam, generally in outside offline sessions what happens, once you written the exam you are leaving that exam, they will told you got some marks, this much marks, they will give that data, and by sticking that result in your notice board, by seeing that you are leaving it. So that is not the correct method. Who will analyze that exam paper thoroughly, and who will test by its own where I done mistake, where I lost the marks. Okay, after that analysis need to prepare a note. Okay, in future not to commit that such type of mistakes. Who will prepare that type of material, that type of analysis, then they will get success. Okay, that is the secret behind the success. So but our students are very busy with their classwork, because they are in most of the students are from third years and final years. They are busy with their project works, seminars, plus some class works. So because of that, we are handling that one by providing a personal coach to you. Your personal coach is take complete care of that. He will prepare that complete note, and based on that they will guide you, and they will prepare proper study plan to you. By following that study plan properly, definitely you get success in your examinations. So my dear students, please think once of it, okay, and get maximum benefits. Okay, now thank you. Now we are moving to our topic. Now we are at overview of PN junction diode. Overview of PN junction diode. Already we completed some topic. So far we completed how to form a PN junction diode, how to construct a PN junction diode, and what are the sequence of events takes place during the formation of the junction. We observed first drift, diffusion, recombination, drift. Okay, now under steady state your junction is like that. Now we calculated the amount of electric field at the junction. Okay, and we derived an equations for this, and after that, by making maximum, see, these are the electric field equations at the junction, and this is the maximum electric field at junction E naught. By equating these two, we got the E naught value, and another relation we got, that is Na into xp naught equals to Nd into xn naught. And after that, we derived an equation for depletion region width W naught. Okay, which is this is the equation for W naught we derived. Now from this I got the extension of depletion region on N side and P side. Okay, so we calculated after that depletion region width also we calculated depletion region width also, and we got that depletion region width is square root of 2 epsilon by q into 1 by Nj plus 1 by Nd into V naught. V naught is the contact potential or built-in potential. Okay, so now in this the unknown parameter is V naught, contact potential, we don't know the value of it. Now we go and derive an equation for this contact potential. Okay, now so I am going to deriving an equation for contact potential. See, under steady state, the current flowing through the junction diode is 0. So diode current is 0. Okay, that means current due to electrons is 0, as well as current due to holes also 0, because no carrier is crossing the junction. Current due to holes also 0. So total diode current is nothing but a sum of electron current plus sum of hole current. And in this you have two components. Similarly in this also you have two components, drift current plus diffusion current. So drift current and diffusion current. Similarly here also drift plus diffusion. So therefore hole current is nothing but a drift current plus diffusion current. Now I am taking current density. Therefore hole drift current density, see, current is nothing but the area into current density. Once it is 0, current density also 0. Therefore J drift by holes plus J diffusion by holes is equals to 0, is equals to 0. Now drift current density is, we know the equation for that. Drift current density equation, that is P into Q into N into, sorry, P into Q into mu P into applied electric field plus diffusion current density is minus Q into dP into dP by dx equals to 0. Now I am taking this one that side. Therefore P into Q into mu P into applied electric field is Q into dP into dP by dx. So here Q gets cancelled. Now taking this mu this side, at the same time I am going to representing the magnitude of electric field is dV by dx. Magnitude of electric field is dV by dx. Okay, now substituting that one here, therefore, and taking this P also this side. Okay, now okay, keep P as usual here, P into dV by dx is equals to dP by mu P into dP by dx. Now dx gets cancelled. We know dP by mu P value is Vt. So now just take P this side. Therefore dV equals to Vt into 1 by P into dP. That is the equation. Now I am applying limits on both sides. So now the equation is integral dV equals to Vt constant into integral 1 by P into dP. 1 by P into dP. Okay, now we need to apply the limits on this. So in that case, limits point of view, this is a dV. Now the limits should be of in terms of voltage. This is a dP. Now the limits should be in terms of P, hole concentration. Now if you check your PN junction, this is P side and N side. This is the depletion region width on P side and depletion region width on N side. It gives a net negative immobile ions, and here it has a positive immobile ions. And here potential we called it V N naught, and net potential here is Vp naught. And we mentioned already contact potential V naught is Vn naught minus Vp naught. Now I am applying limits. Sorry sir, sorry for disturbance. Outside some disturbance is going on. I am very sorry for that. Now dV. So I am moving from P to N. Vp naught to Vn naught I am taking limits. Vp naught to Vn naught. Now limits on dP. P side to N side. In P side, hole concentration in P side is Pp, and hole concentration in N side is, hole concentration on P side is Pp, hole concentration in N side is Pn. So this is a Pp to Pn. Pp to Pn. Now simplify this. Now it became integral dV is V. Limits are Vp naught to Vn naught equals to Vt into integral 1 by p, that is ln of p, and limits are pp to pn, pp to pn. Now it is vt into ln of pn, ln of pn, k, minus ln of pp, k, ln of pp. And one more thing, and just a minute, here we did not, this is a no need to take magnitude because they did not specify it is a magnitude. You take the correct value, correct polarity. E is, we know that, minus dv by dx. Now it is minus minus. Now after that it is minus. Here we have minus. Now it is minus of Vn naught minus Vp naught. Okay, so take this minus this side. Now Vn naught minus Vp naught is nothing but a V naught. We know that V naught equals to Vt into ln of Pp minus ln of Pn, ln of Pn. Okay, now so finally V naught is Vt into ln of Pp by Pn. From this we can write Pp equals to Pn into e power V naught by Vt. This is called law of junction. We call it as law of junction. Law of junction. This is law of junction. Now we know the values of Pp and Pn. That means a doping on p side in hole concentration in p side and electron concentration in n side. So we know the values. Just substitute that. We know Pp is amount of doping on p side Na, and Pn is Ni square by Nd by applying mass action law. Ni square by Nd by applying mass action law. Okay, now take these values, substitute here in this V naught. Therefore contact potential is V naught equals to Vt into ln of Pp means Na into Na by Pn. Pn is Ni square by Nd. Ni square by Nd. Here. This is the equation for contact potential V naught. Okay. So this is important equation. So we are using this equation. We are going to use this equation frequently while solving the problems. Okay, this equation is very, very important. Okay, now so far we derived so many equations. Now that equations I am writing at one point. So I am giving first one is depletion region width, contact potential we derived V naught equals to Vt into ln of Na Nd by Ni square, Na Nd by Ni square, and depletion width W naught is square root of 2 epsilon by q into 1 by Na plus 1 by Nd into P naught. And extension of depletion region on P side xp naught is W naught into N d by Na plus Nd, Nd by Na plus Nd. Similarly, Xn naught is W naught into Na by Na plus Nd, Na plus Nd. And we have another equations for electric field. E is equals to minus Na into maximum electric field E naught equals to minus Na into Q by epsilon into xp naught, or which is equals to, and another value for E naught we have, so I am writing that one also, that is minus Nd into Q by epsilon into xn naught. Okay, and there is a equation for electric field also, that electric field is minus Na into Q by epsilon into xp naught into 1 plus x by xp naught from minus xp naught to 0, and minus Nd into Q by epsilon into xn naught into 1 minus x by xn naught. So this is for minus xp naught to 0, and this is for 0 to xn naught. So these are the equations for this. Okay, so these are the different equations what we have. And one more thing, don't forget, here your diode is under open circuit condition, under open circuit condition, no biasing voltage applied, under open circuit. Now we know that in reverse bias depletion region width is increasing, and in forward bias width is decreasing, finally it became 0. Let us, the applied voltage in forward bias is less than the cut-in voltage or threshold voltage. Okay, cut-in voltage or threshold voltage. In that case, what happens is some depletion region width is existing at the junction even in forward bias also. If they applied, see, we know the plot, this is the Vi plot what we have, Vi plot in forward bias. Okay, this is the plot what we have, this is the cut-in voltage V gamma. If the applied voltage is less than this value, here there is no current, that means some depletion region is existing, some depletion region is there here in this region. From this point onwards your depletion region is approximately 0. Okay, here some depletion region is existing, some depletion region width is there even in forward bias also. Okay, but the depletion region width here is less than the depletion region width under open circuit conditions. Okay, and one more, this is the plot in reverse bias, and in this the depletion region width is increasing, W is greater than in this case compared to open circuit condition, W value. Okay, so that is the condition or variation in depletion region width with respect to applying biasing condition. Okay, let us assume even though your diode is forward bias or reverse bias, but even in forward bias it is less than V gamma. Okay, now I am going to writing the whatever the expression so far you've written this side, the same expressions I am going to be representing, under biasing conditions. That means for a biased diode, how these expressions are going to be changing. Now I am going to representing that. Okay, now see here I am going to representing this one for. So some commonalities is there, we need to specify that. So first I am going to taking, so this is for this is open circuit. Now this is for a biased diode. That means forward as well as reverse biased diode. Okay, no change in contact potential. So whatever the equation V0 here you have, same V0 you have to write for this. V0 equals to Vt into ln of NAND by Ni square. That is the V0. Okay. Sorry. Now W value, I am going to representing W value here by, I am representing W value by W. Okay, here I am going to classifying this into two parts, under reverse bias and forward bias. Reverse bias and forward bias. Now the equation for W here is, so W is depletion region width, the W is in reverse bias square root of 2 epsilon by Q into 1 by Na plus 1 by Nd into V0 plus applied reverse voltage VR. Just take the magnitude of that. V0 plus VR. In forward bias, you can write depletion region with this square root of 2 epsilon by Q into 1 by Na plus 1 by Nd into V0 minus applied forward voltage Vf. That is the equation. Okay, sir. Now only this is the point where you need to differentiate forward bias and reverse bias. Okay. Sorry. Now in forward bias, this is the expression you need to use. In reverse bias, this is the expression you need to use. Okay, now I am going to writing the remaining equations. Now xp0 became xp, I am writing xp0 by xp. Now w0 became w as usual, nd by na plus nd. If your diode is in forward bias, you can use this. And one more thing, sir, here there is a condition, the applied forward voltage should be less than V0. In that condition only it is valid. Okay, because in that condition only, at that condition only, we have some depletion region even in forward bias. So this is the xp value. Just xp0 became open circuit conditions under, now xp became under biased condition. Now in reverse bias, you can use this W value. If it is in forward, you can use this W value. That's it. Next, similarly xn is W into Na by Na plus Nd. Okay, and after that E naught, maximum electric field is E naught, maximum electric field is minus Na into Q by epsilon into Xp, and which is minus Nd into Q by epsilon into xn, not xp. You will get the values of xp and xn from this. And there is an equation for electric field also in that is minus Na into Q by epsilon into xp into 1 plus x by xp. This is the case for x value is greater than or equal to xp, less than 0, and which is minus Nd into Q by epsilon into xn for into 1 minus x by xn for x value greater than 0, less than or equals to xn. That's it. So these are the equations when your diode is under biasing conditions. Okay, so these are the equations for open circuit and the same equations under biasing conditions. Here biasing means first calculating the contact potential V0. V0 is Vt into ln of Na Nd by Ni square. And in reverse bias, this is the equation for depletion region width W0. Okay, depletion region width W0. Sorry sir, a small disturbance. Now so I got one message, Amit Kumar Pandey sir. Hello sir, thank you, thanks for joining. So these are the expressions for these are the maximum expressions in PN junction diode. Okay, so this screen is what you are now, whatever the screen you are viewing here, this is very important sir. Okay, this screen is very useful to you. So most of the problems in PN junction diode are going to be depend on this. Okay, in addition to this, there are current equations. Okay, and during derivation of the current equation of a PN junction diode, intermediate conditions. Okay, at intermediate level, we get few equations. They are the amount of charge injected from P region to N region, or amount of charge injected from N region to P region. Now they may ask in terms of a charge or in terms of a carrier concentration. Okay, they may ask any one of that. Okay, so but if you know these equations, 50% of the equations part in PN junction diode is completed. Okay, so during solving problems we are going to using these equations mostly. Now next I am moving to next topic. So for we observed when PN junction diode is under reverse bias, under open circuit, what are the equations, and once we are familiar with what are the equations in open circuit, how to convert those equations for a biased PN junction diode, just we completed that. Okay, now I am going to giving the most important topic, that is that is current components in a forward biased PN junction diode. Okay, so now current components in a forward biased PN junction diode. So current components in a forward biased PN junction diode. Current components in a forward biased PN junction diode. Okay, now we are going to discussing about this topic, current components in a forward biased PN junction diode. See, we know that what is the meaning of forward biasing here. Simply P connected to positive terminal of the battery and N connected to negative terminal of the battery. Fine. Now, so this is our PN junction diode. So this is the P region and this is the N region. In forward bias, you can treat the applied forward voltage is more than the cut-in voltage, so no need to represent the depletion region. And the important thing is here P connected to positive terminal of the battery and N connected to negative terminal of the battery. Okay, this is the applied forward voltage. Applied forward voltage. Okay, now see, now I am going to representing the, in P side we have holes are majority charge carriers and in N side electrons are majority charge carriers, and in P side electrons are minority charge carriers. Now I am going to representing that minority carrier concentration. This is the number of minority charge carriers exist in P side under steady state condition or thermal equilibrium condition. Now you can treat one thing. You can always assume we are performing the operation at a constant temperature. That is very, very important. At a constant temperature. Okay. Now in N region, let us, this is the amount of hole concentration. Amount of hole concentration. They are minority charge carriers, and we are representing this one by in general. In general, we represent it as N P naught, and this is P N naught. N P naught is the electron concentration in P region under steady state. Now P N naught is hole concentration in N region under steady state condition. That is the meaning of it. Okay. Now once you operate like this, that means P connecting to positive terminal of the battery and N connecting to negative terminal of the battery. Okay, what happens is, now an electric field is, due to this positive and negative, an electric field is directed from P region to N region. An electric field is directed from P region to N region. Due to this electric field, carriers are moving, and we know that holes always move from p region to n region, and electrons move from n region to p region. Why? Because always hole movement is in the direction of electric field, and electron movement is opposite direction of movement of electric field. So because of that, whatever the holes you have in p region, what you have in p region, majority charge carriers, they move from p region to n region. They are moving from p region to n region. This is the movement of the holes. Now holes are entered from p region to n region. Now this whole movement from p region to n region is like, this is the movement of holes due to the external electric field. So your whole movement is once due to electric field. Now that movement is, we called it by drift movement. This is the drift movement. That is drift movement. And at the same time, so okay, now we discuss only with whole movement. Later we apply the same to electron movement in n type and p region. Now you observe one thing. This is the whole concentration under steady state in n region. With the drift movement, this much number of holes are injected from p region to n region at junction. Now this is the total whole concentration at junction. Whole concentration at junction is this one. This is the whole concentration at junction. But you observed at this end less amount of holes, at this point high amount of holes. Now there is a concentration gradient in a n-type semiconductor in terms of hole concentration. Due to this concentration gradient, holes diffuse. Holes are going to diffuse from n region to p region, n region, from junction to towards n region. They are going to diffuse. They are diffuse in this direction. Okay, this is the diffusion. So they are going to diffuse. Now diffusion is taking place. So electrons starts moving from junction to towards the n region. In that movement, already we know this is a n-type semiconductor, and in n-type semiconductor, electrons are the majority charge carriers. Electrons are majority charge carriers. Now during the diffusion process, these holes are going to recombine with the electrons which are available in n region. Due to that recombination, whole concentration is decreasing exponentially. Decreasing exponentially. Okay, decreasing exponentially. Sorry. Now hole concentration is decreasing exponentially because holes are trying to move this side, electrons are coming this side. During that moment, recombination is taking place. Recombination in this sense, it is going to forming a covalent bond. Now whole concentration is changing exponentially like this. It is decreasing exponentially. Finally it reaches the steady state value. Okay, Now here you observe one thing. This is the region. So the yellow color one is, this is the movement of excess charge carriers, because these charge carriers are not available initially in n region. Only this much number of holes are available in n region initially. Okay, that's why these charge carriers are called as excess charge carriers. Excess charge carriers. Excess or injected. Okay, excess or injected charge carriers. Excess or injected charge carriers. Okay. Now in that process, this carrier concentration is high at junction. By moving towards n region, it is recombination is taking place. Because of that, its concentration is decreasing exponentially. So once its carrier concentration is decreasing exponentially, goes on, whole diffusion current is going to be decreasing. Okay. Now the way how your whole movement is in p region and n region, similarly the electron movement is a similar way in n region and p region. Now first electrons are going to be drifting here. By drift they entered into n region, they entered into p region. Okay, and after that, once they drift into that, they are going to be diffuse in p region like this, and due to recombination, concentration is going to be decreasing, and we called this is the excess charge carrier concentration or injected carrier concentration, this red part. Okay, now here this is the drift movement of electrons. Drift. Here diffusion. During diffusion process, what happened here? Recombination taken place. Diffusion followed by recombination here. Now see this. There is a question in GATE examination, previous GATE examination, that is, what are the sequence of events takes place in a forward biased PN junction diode? Once again I'm repeating, sir. What are the sequence of events takes place in a forward biased PN junction diode? That is the question. Now see, you can easily answer for that question. See, first event is, see, first hole is drifting. With the drift movement they entered into n region. Due to concentration gradient they are diffusing. During diffusion, recombination of carriers are taking place. Now the first event is a drift, and drift also called as injection. And the second one is diffusion. And third one is recombination. See, similar type of events we observed in under open circuit condition also. Under open circuit condition also, first diffusion, next recombination, and last we have a drift. And these sequence of events are repeating up to the net current passing through the junction is 0. Up to that point it is continuous. Okay. Now So these are the sequence of events takes place when your PN junction diode is under forward bias. Okay, now I am going to representing the current components. These are the movement of charge carriers. So far we studied how your charge carriers are moving, in which direction they are moving, with what is the movement. It is a drift movement or diffusion movement. So far we completed that. Okay, and let us these are the electrons which are available, majority. Now the same thing I am going to be converting in the form of a current components. So holes are moving this side, current also in the same direction. If electrons are moving this side, current is due to movement of electrons, and current movement is opposite direction. Current is moving in opposite direction. Now I am going to that. So for reference I am keeping this one here, or keep this side. Yeah, see, now I am going to PN junction diode. So now I am writing that events here. First one is a drift movement, and we called drift also injection. We called drift also, we called it by injection. The second one is diffusion, and the third one is recombination. These are the sequence of events takes place. Okay, now I'm going to writing another PN junction to represent the current components. Okay, for better understanding purpose, I'm going to separating a plane to N region and P region, because don't think this is not a depletion region. This is not a depletion region. A plane which is separating P region and N region. Okay, to understand effectively what is happening actually in P region and what is happening actually in N region, for understanding that understanding purpose. Okay, now first I am going to writing the hole movement. Holes are moving this side. This is the hole movement. Holes are moving this side. Once they enter this much number of holes, they are going to be diffusing. Holes are going to under, these are the under steady state hole concentration is this one. Now holes are diffusing once entered in, this is P region and N region. Once holes are entered into N region, we observed they are diffusing like this. They are diffusing like this. So sir, this plot also important, how they are diffusing everything, because later in problems they give different diffusion phenomena. For let us take A diode and another diode B like this. Now based on this diffusion, you need to calculate which diode is having highest potential applied, where lowest potential is applied, those things. Okay, see, if this is the highest potential, if high voltage is applied, high amount of more number of holes are injected. Okay, if low voltage is applied, low amount of holes are injected. Okay, the amount of excess charge carriers is varying with respect to applied forward voltage. If high amount of forward voltage you are applying, high amount of excess charge carriers are injected into the N region from P region, and if low voltage you are applying, low number of carriers are injecting. Okay, Now this is the whole movement. Okay, for your understanding, clarity, this is the whole movement. So holes are moving like this, holes are moving like this, these are the holes. Now I am going to writing the whole current. Once holes are moving this side, whole current is moving the same side, whole current is moving in the same direction, same direction, whole current. This is the whole current, whole current. Similarly, holes are moving this side and whole current is this direction. This is the whole current. Okay, now I am calling this current is IPP of X, IPP of X, and this is IPN of X, IPN of X. IPP of X is the whole diffusion current, whole diffusion current in IPP of X, whole drift current in P region, and IPN of X is the whole diffusion current in N region. Whole drift current in P region, whole diffusion current in N region. Similarly, I am going to representing the electron movement. Now electrons are going to be diffusing. First drift movement of electrons takes place in this side. This is the drift movement of the electrons. Okay, so drift movement of the electrons, and once electrons entered into this, they diffuse. See, under steady state, these are the minority electrons in P region. Now once electrons entered into this, they are going to be diffusing like this, like this, like this. Now so this is the direction of the electrons. These are the electrons. So these are the electrons. This is the electron movement. Sorry. Now once that is the electron movement, current is moving opposite direction to the electron direct movement. Now it results a current like this. Now current is moving like this. This is the current direction. And here this is the current direction. And now we can write it as I N P of X, and this is I N of X, N of X, I N of X, I N P of X and I N of X. Now whatever the currents here you mentioned so far, I am going to writing that values, that names here. The first one is first current component is I. Now first one is IPP of X. This is whole drift current in P region, whole drift current in P region. Whole drift current in P region. Similarly, second component we have INN of X. That is electron drift current in N region. electron drift current in n region. Electron drift current in n region. And third one is INP of x. NP of x, that is electron diffusion current in p region. Electron diffusion current in p region. Diffusion current in p region. Similarly, there is a current IPN of x, that is also whole diffusion current whole diffusion current in n region. Sorry sir, sorry for disturbance. Whole diffusion current in n region. Okay, so these are the different current components present in a forward biased PN junction diode. IPP of x, INN of x, INP of x, and IPN of x. Whole drift current in P region, electron drift current in N region, and electron diffusion current in P region, and whole diffusion current in N region. If someone asked you what is the diode current, is it a drift component or diffusion component? Now, the diode current is, at any point, diode current is sum of these two components at that point. For example, at this point, there is no diffusion current because diffusion is completed up to here. Now only you have this component, so only drift component. Here also only drift component, no diffusion. So at extreme end of P region, diode current is equals to IPP of x, that means whole drift current. At extreme end of N region, diode current is electron drift current only. Okay, similarly in P region, diode current is IPP of x plus INP of x, and in N region, INN of x plus IPN of x. And at junction, let us take this is the junction. At a junction, holes are going to be diffusing, and similarly electrons are diffusing. Okay, this one, yeah. So at junction, whole diffusion current plus electron diffusion current, that is the diode current at junction. At junction, diode current is sum of whole diffusion current plus electron diffusion current. So these are the different diode current equations. Based on the location, the amount diode current value is not changing, but components is changing, or component value is changing. Okay, if one component is increasing, other component is going to be decreased. Finally, the net value is going to be a constant from P region to N region. Okay, now I am writing the diode current equations at a different location, different possible current equations. First, diode current is equals to IPP of x. Sorry sir, sorry for disturbance, what was happened at outside. IPP of x, this is at extreme end of P region. At extreme end of P region, and INN of x at extreme end of n region, and IPP of x, see, at this point IPP of x plus INP of x, NP of x, this is in P region. Similarly, INN of x plus IPN of x, this is in n region. Here this one plus this one, INN of x plus IPN of x, and at a junction, that is IPN of 0, x value is 0 because it is a junction, plus INP of 0. So this is at a junction. So this is the diode current. All are diode current equations. You can use any one of the equation to calculate the diode current equation. Okay, if you observe one thing, in first two cases they are purely drift components, but there is no fixed value for x value is changing. Now next to two values are combination of drift plus diffusion, there also x value is changing, and the last component x value is fixed constant, it is at x equal to 0. So once x value is 0, it is easy to us to calculate. That's why I am going to using this equation to calculate the diode current. I am using this equation to calculate the diode current. Okay, sir. So my dear students, if someone asked you what is the diode current equation or diode current components, is it a drift or diffusion, then immediately you have to give all these possible conditions, total 5 possibilities. At extreme end of P region, whole drift current. At extreme end of N region, electron drift current. In P region, whole drift current plus electron diffusion current. In N region, electron drift current plus whole diffusion current. At a junction, whole diffusion current plus electron diffusion current. These are the different possible diode current equations. Okay, sir. So my dear students, please be careful. In competitive exams, they may ask diode current. What is the diode current in P region or N region? They may ask any one of this. Okay, at that time, be confident. If you understand this concept thoroughly, you can easily understand that. Now I am going to using this concept, this equation now to calculate the diode current equation. Yeah. Now diode current equation. Diode current equation. Diode current equation. Okay, just before we've written, we finalize the diode current equation is represented by sum of whole diffusion currents at junction, the electron diffusion current at junction plus whole diffusion current IPN of 0 at a junction. Okay, now first I am going to calculating IPN of 0. IPN of 0 first I am going to calculate it. This is whole diffusion current, whole diffusion current at junction. At junction. First I am going to calculating this one. Okay. Now that is, we know one thing. Whatever the diode we have here, so let us take the diode like this. In forward bias, no matter of depletion region. Okay, so yeah. Now there is a cross-sectional area of the junction or diode, that is A. Now I am, instead of taking current, I am taking current density. Okay, that means I am representing, we know the current density value, diffusion current density. So based on that, first I am going to calculating IPN. IPN is equals to JPN, whole diffusion current density, into area, cross sectional area. Now A into, there is a equation for diffusion current density. What is the diffusion current density equation? That is minus Q into dP into dP of x by dx, or dP by dx. Now with respect to x, we are going to be discussing x-axis. That's why I am going to adding a subscript x to this, dP of x by dx I am adding. Okay, now IPN can be written as minus A into Q into dP into dP of x by dx. But we need IPN of 0. IPN of 0, not IPN at junction. Now these three are constant with respect to x, because throughout the semiconductor these three are constant. Area no change, charge of the electron no change, diffusion coefficient of holes is constant, but this is changing now, P of x. So we need this value at x equals to 0. Okay, now get the value of dP of x by dx at x equal to 0, substitute that one here, then you get IPN of 0, whole diffusion current in N region. Okay, now so now our equation is IPN of 0 equals to minus A into Q into dP into dP of x by dx at x equals to 0. Yeah. First we should know P of x, whole concentration with respect to distance. See, that too, that is in N region. So for that I am taking the junction. Here is the junction. Now I am concentrating mostly on N side. Under steady state, whole concentration is this one in N region. Yeah. Now here, this is P region and this is N region. N region. Okay. and this is under steady state hole concentration in N region, Pn naught. Under steady state hole concentration in N region, Pn naught. Now let us this much number of this much number of holes are injected from P region to N region. Okay, now these holes are diffusing in N region. Diffusion takes place in N region. Diffusion takes place in N region. During the diffusion process, these holes are recombined with electrons which are available as a majority charge carriers in N region. Their concentration is going to decrease. Their concentration is going to decrease exponentially like this. Sorry. So exponentially concentration is going to decrease like this. Finally, they reach the steady state value. This is the injected or excess carrier concentration. Excess carrier concentration. Okay, this one. Now this is the whole concentration in N region with respect to distance x. Now from this we can write P of x equals to P of x equals to, from here to here it is Pn naught plus the value of this one, this plot. Now let us take this one. At junction, the excess or injected carrier concentration is P dash of 0. Now we can define this plot by P dash of 0 into e power minus x by Lp, because it is decreasing exponentially with respect to distance in N region. Therefore, now the total equation P of x is Pn naught plus P dash of 0 into e power minus x by Lp. That is the equation for P of x. So far we get the equation for P of x. Now just substitute that one. Okay, substitute that one in this. That means differentiate this with respect to x and substitute x value after that. Therefore, dP of x by dx is, just I am differentiating that. This is constant. Once it is constant, differentiation is 0 plus differentiation of this one is P dash of 0 at junction, injected value also 0. It is not changing with the distance. Okay, at junction it is 0. Now e power minus x by Lp, differentiation is e power minus x by Lp into minus 1 by Lp. So its value is minus P dash of 0 by Lp into e power minus x by Lp. That is the dP of x by dx. dP of x by dx. Now in this, but we need at x equal to 0. So therefore dP of x by dx at x equals to 0 is minus P dash of 0 by Lp into e power minus 0. It is 1. Therefore final value is minus P dash of 0 by Lp. Just take this one, substitute in your equation. Therefore IPN of 0 is equals to IPN of 0 equals to A into minus Q into dP into, our equation is dP of x by dx at x equals to 0. That is our condition. Now just substitute the value of this one. It is minus A into Q into dP into this value is minus P dash of 0 by Lp. Now after simplification you get that IPN of 0 is minus into minus plus A into Q into dP into P dash of 0 by LP. This is the equation for IPN of 0. In this equation, if you observe P dash of 0, that is the excess or injected carrier concentration at the junction. Excess or injected charge carrier concentration at the junction. Okay, now that is IPN of 0. So already at the same time we derived an equation for P of x, that is Pn naught plus P dash of 0 into e power minus x by LP. Okay, now from this I am taking at x equal to 0 at a junction. At a junction, it means at x equals to 0. At x equals to 0. At x equals to 0, we can write it as P of 0. That means total hole concentration at a junction equals to Pn naught plus P dash of 0 into e power minus 0 by L. So this is 1. Therefore, P of 0 is Pn naught plus P dash of 0. Now from this we can write P dash of 0 is P of 0 total hole concentration at junction minus Pn naught under steady state minority carrier concentration in N region. Now substitute this one here. Therefore, next level of equation IPN of 0 is A into Q into dP by LP into P of 0 minus Pn naught. P of 0 minus Pn naught. Okay, so that is the value of Pn naught. Now we need to calculate P of 0, total injected, so the total hole concentration at junction. Okay, now I am going to taking that equation. I Pn of 0 is finally A into Q into dP by LP into P of 0 minus Pn naught. Okay, now we need to calculate this. This is the at present equation. At present, this is our main equation. At present, take the value of P of 0, substitute in that. For that, now I am going to take the help of law of junction. What is our law of junction? Law of junction. So from law of junction, we can write PP equals to Pn into e power V naught by Vt. Okay, now first I am applying this one to a open circuited junction. For open circuited junction, we know PP equals to Na, majority carrier concentration in P region, and Pn equals to Pn naught, steady state, under steady state hole concentration in N region, Pn is. Okay, now take these two, substitute in this. Therefore we can write Na equals to Pn naught into e power V naught by Vt. Okay, so this is the equation. under open circuit conditions. Under open circuit conditions, this is the equation. Okay, now I am going to representing for a bias diode, and that too one more thing, sir. Just you can assume a P plus N junction. P plus N junction you need to assume. You need to use P plus N junction. That means P is doped heavily compared to N region. Okay, P is doped heavily compared to N region. That is the meaning of that. So Na is Pn not into e power V naught by Vt. Fine. Now this is for a in forward bias. In forward bias, Pp whole concentration in P region is Na because heavily doped it is, no change, and electron concentration in P region. Electron concentration in P region is P of 0. P of 0. Why? Because now this is nothing but a, in this is the distribution of the carriers in N region. Holes are distributing like this. Here we have, this is the total concentration at a junction. This is the total concentration of holes at a junction in N region. Clear? Now they are diffusing in this side, but at junction they are this much value. Okay, so Pn is whole concentration in N region is P of 0. Now take the, and one more thing, important point is V naught. In place of V naught you have to write barrier potential. Okay, so that is the junction potential also we called it. Now when it is forward bias, V naught can be written as V naught plus Vf, whatever the forward voltage you applied. V naught plus Vf you need to apply. Okay, therefore, and V barrier is, barrier voltage is V naught, okay, minus Pf forward voltage, applied forward voltage. Now therefore the, I am substituting these things in this equation. Na equals to Pn is P of 0 into e power. Actual equation is, in place of this you need to write V barrier. Okay, under open circuit conditions, V barrier equals to V naught contact potential. Okay, and in forward bias it is V naught minus Vf. In reverse bias it is V naught plus Vr. So P of 0 into e power, barrier is V naught minus Vf. V naught minus Vf by Vt. Now this is the second equation in this. Both are representing the Na. Now I am going to equating both the equations. Just equating both the equations. Therefore Pn naught into e power V naught by Vt equals to P of 0 into e power V naught minus applied forward voltage by Vt. So it is Pn naught into e power V naught by Vt equals to P of 0 into e power V naught by Vf into V naught by Vt, sir, into e power minus Vf by Vt. In this one and this one gets cancelled. Now take this one this side. Therefore P of 0 equals to Pn naught into e power Vf by Vt. Okay, now this is nothing but a hole concentration at a junction, okay, in N region. Hole concentration at a junction in N region. Now substitute this one in our main current equation. Our current equation previous case is IPN of 0 is AQ dP by LP into P of 0 minus Pn naught. Just substitute this value of P of 0 in this. Therefore IPN of 0 is A into Q into dP by LP into P of 0 is nothing but a Pn naught into e power Vf forward voltage by Vt minus P of 0 and Pn of 0. By simplification, we can write IPN of 0 is A into Q into dP by LP into Pn naught into e power Vf by Vt minus 1. This is the whole diffusion current in N region at junction. Whole diffusion current at junction. Okay, whole diffusion current at junction. Next, now I am writing similarly we can write I NP of 0 is A into Q into dN by ln into NP naught into e power Vf by Vt minus 1. Okay, therefore our diode current ID is equals to IPN of 0 plus INP of 0. Add these two. Therefore, by adding A into Q into dP by LP into Pn naught into e power Vf by Vt minus 1 plus INP of 0, which is A into Q into dN by ln into NP naught into e power Vf by Vt minus 1. Okay, just I am taking common. Therefore, ID is AQ into this one. I am taking common. Therefore, A into Q into dP by LP into Pn naught plus dN by ln into NP naught into e power Vf by Vt minus 1. Now I am repeating the same equation here. Therefore, our diode current is A into Q into dP by LP into Pn naught plus dN by ln into NP naught into e power Vf by Vt minus 1. Vf by Vt minus 1. Now this part we called it as a reverse saturation current. Now I am representing this one by simply I naught. Therefore, diode current ID is I naught into e power Vf by Vt minus 1. In general, now I am taking, this is ID, now I am taking Vf is Vd. Let Vf equals to Vd. Now ID is I naught into e power Vd by Vt minus 1. A little bit modification I am doing, and one additional parameter here I am going to add, that is ideality factor. Therefore your ID is I naught into e power Vd by eta Vt minus 1. Vd by eta Vt minus 1. Here eta is ideality factor. Ideality factor, which is 1 for germanium and 2 for silicon. Okay, if they mention some value we take it, otherwise in general we take it as 1 for silicon also at high current values. Finally, this is the current equation for ID. Okay, so my dear students, please be concentrated on this equation. So okay, in future sessions we are going to solving the problems on this current equation. ID is I naught into e power Vd by eta Vt minus 1. Okay, just a minute, we look on to this current equation, I naught value. So whatever the I naught there you mentioned is, you mentioned I naught as, just before you written I naught value is A into Q into dP by Lp into Pn naught plus dN by Ln into Np naught. And we know Pn naught is the whole concentration in N region, which is Ni square by amount of doping in N side is Nd. And similarly we know the value of Np naught, which is Ni square by Na. Just take these values, substitute here. Therefore I naught is A into Q into dP by Lp into Ni square by Nd plus dN by Ln into Ni square by Na. Ni square by Na. So all of you should be thorough with this equation for I naught. Now I am doing little bit modification on this, taking Ni square common. So A into Q into Ni square into dP by Lp into Nd plus dN by Ln into Na. This is the equation for I naught. Okay, so this is the equation for I naught. Sorry sir, some disturbance at outside. I'm very sorry for that. Now this is the equation for I naught, and sometimes they give the data, they may not provide the L value, because we know that the diffusion length of the electrons is square root of dN into tau n, and Lp is square root of dP into tau p. Okay, just take the values of those two, substitute in that L value, you get it, or you may represent that one in terms of that also. Now I am writing that equation also. Just I am going to replacing this L by root D into tau. By replacing that, you get I value, I naught value is A into Q into Ni square into 1 by Nd into square root of dP by tau p plus 1 by Na into square root of dN by tau n. That is the value. That is another equation for I naught. Okay, so like that you can define diode reverse saturation current. And one more thing, here we've written I naught, id is I naught into e power Vd by eta Vt minus 1. Okay, just by simplification, it is Id equals to I naught into e power Vd by eta Vt minus I naught. Take this I naught this side. Therefore, Id plus I naught is equals to I naught into e power Vd by eta Vt. If you observe one thing, this is of the order of milliamperes. This is of the order of microamperes based on the diode. For silicon it is nanoamps, for germanium it is microamps. But anyway, compared to ID it is 1000 times less. So ID is much greater compared to I naught. Therefore, ID is much greater than I naught. So compared to this, you can neglect this value. Therefore, after that, you can write your ID value is approximately I naught into e power Vd by eta Vt. This is the approximate equation for ID. Approximate value of ID. Okay. So this is about diode current equation. Okay. Next session we discuss about charge, amount of charge entered into the N region to P region or from P region to N region. Okay, in depletion region amount of charge exists, and we discuss those things while discussing in detail about forward bias and reverse bias and the effect of temperature on VA characteristics and calculation of depletion region, calculation of transition capacitance and diffusion capacitance. These are the topics left in our PN junction diode. Probably by next session we complete those things. Okay, just I am going to rewinding just a minute. Wait, I will remind the topics today what we discuss. So we start with the overview of PN junction diode, and after that we discuss how to get the PN junction diode. First, we take in an intrinsic semiconductor, and in that semiconductor we mark a line at center, half side doped with n-type, a third group impurity, half side doped with fifth group impurity. Now one side became p-type semiconductor, another side became n-type semiconductor, and after that we replace the p region by its equivalent representation with the negative immobile ions, holes and free electrons. Similarly, n-type, n side positive immobile ions, and this one positive immobile ions, free electrons and holes. So in this we observed there is a concentration gradient. Due to that concentration gradient, diffusion movement of carriers takes place. Diffusion movement of carriers takes place. Once a diffusion movement is taken place, a diffusion current is flowing through the junction. Now that is due to majority charge carriers, and after that a recombination is taking place during the diffusion movement. After recombination across the junction, we observed only immobile ions. We call that region is space charge region or depletion region. It results now across the junction, the depletion region exhibits a dipole moment, and it affects an electric field is directed from N region to P region. Due to this electric field, a drift movement of carriers takes place. Now due to that drift movement, carriers are moving. Electron is moving from P region to N region and hole is moving from N region to P region. Now these are the minority charge carriers. This is the minority carrier movement. Okay, Now minority carrier movement is taking place at the junction. So after that, now again you observed there is a finally two movements takes place at the junction, diffusion movement and drift movement. Initially drift movement is very high and diffusion movement is sorry. Sorry sir, an unexpected event taken place. Yep. Now see this. Initially diffusion current is high and drift current is low, because the drift current is due to minority charge carriers and diffusion current is due to majority charge carriers, and the direction of currents also like this. Okay, again we observed a concentration gradient. Due to this diffusion movement takes place, but the diffusion movement in this case is less than the diffusion movement in the first case. So that means due to drift movement of the charge carriers. Now it results diffusion current is going to decrease and recombination takes place. After that, a depletion region width increasing, that means strength of the electric field is going to be increasing. Due to this, the drift movement is increasing. Once like that, drift current is going to increase and diffusion current is going to decrease. After some time, both are equal in magnitude. Due to opposite in direction, the net current passing through the junction is zero. Then we said our junction is under steady state condition. Okay. Now, here is the junction under steady state, and we called it as a depletion region with W0 under open circuit. XP0, 0 to XP0 is the extension of depletion region on P side, and 0 to XN0 is the extension of depletion region on N side. And after that we've written the rho V, volume charge density. Because of this uniformly doping, these are uniformly doped junctions. Okay, in uniformly doped junction, P side is a negative immobile ions, that is minus Na into Q. Similarly in N side there is a positive immobile ions, that is minus Nd into Q. So rho V we defined. After that we are going to define the electric field E. Okay, by using Poisson's law we defined the electric field here. This is the electric field representation. This is the Poisson's law, d square V by dx square equals to minus rho V by epsilon. Okay, and from that we define the electric field. We know E is equals to minus dV by dx. So d square V by dx square is like this, and finally dE by dx is rho V by epsilon. Now from that we derived an equations for that electric field. These are the equations. From that it is clear that it is a from minus xp0 to 0, it is anyway straight line, but it is with a negative slope, and from 0 to xn0 it is a straight line again, but it is with positive slope. Okay, so here are the derivations we done. These are the derivative part complete we done, and we derived finally electric field and maximum electric field also we derived. From that maximum electric field we defined Na into xp0 equals to Nd into xn0, and after that from that we derived extension of depletion region on P side and extension of depletion region on N side. Okay, by using that we calculate the depletion region width. Okay, so these are the, so after that we calculated contact potential. So this is the session, today's session. Now I'm winding up this today's session. and today we have another session. In that session I have read over the remaining topics we have in PN-Junction Diode. Okay, we cover the remaining topics in PN-Junction Diode. Now once again I'm thanking to one and all for spending your valuable time with us. Don't forget to subscribe us, and use my code VRAO10 during subscription to get 10% of discount. And please click on this bell icon button, to get the updates of our upcoming videos. And please your valuable comments on YouTube, okay, to provide energy to us and strengthen ourselves. And once again I'm welcoming you all to India's largest online learning platform, Unacademy. Now thank you very much for spending your valuable time with us. Thank you.